An escalator is a moving staircase, a conveyor transport device for carrying people between floors of a building. The device consists of a motor-driven chain of individual, linked steps that move up or down on tracks, allowing the step treads to remain horizontal. Escalators are used around the world to move pedestrian traffic in places where elevators would be impractical. Principal areas of usage include department stores, shopping malls, airports, transit systems, convention centers, hotels, arenas, stadiums and public buildings. Escalators have the capacity to move large numbers of people, and they can be placed in the same physical space as one might install a staircase. They have no waiting interval, they can be used to guide people toward main exits or special exhibits, and they may be weatherproofed for outdoor use. A non-functioning escalator can function as a normal staircase, whereas many other conveyances become useless when they break down. Design, components, and operation. Operation and layout. Escalators, like moving walkways, are often powered by constant speed alternating current motors and move at approximately 1–2 feet per second. The typical angle of inclination of an escalator to the horizontal floor level is 30 degrees with a standard rise up to about 60 feet. Modern escalators have single-piece aluminum or stainless steel steps that move on a system of tracks in a continuous loop. Escalators have three typical configuration options: parallel, crisscross, and multiple parallel. As a safety measure, escalators are required to have moving handrails that keep pace with the movement of the steps. This helps riders steady themselves, especially when stepping onto the moving stairs. Occasionally, the handrail will move at a slightly different speed from the steps, causing it to creep slowly forward or backward relative to the steps. The loss of synchronization between handrail and step speed can result from slippage and wear. The direction of escalator movement can be permanently set, or be controlled by personnel according to the predominant flow of the crowd, or be controlled automatically. In some setups, direction is controlled automatically by whoever arrives first, whether at the bottom or at the top. Design and layout considerations. A number of factors affect escalator design, including physical requirements, location, traffic patterns, safety considerations, and aesthetic preferences. Foremost, physical factors like the vertical and horizontal distance to be spanned must be considered. These factors will determine the length and pitch of the escalator. The building infrastructure must be able to support the heavy components. The escalator should be located where it can be easily seen by the general public. In department stores, customers should be able to view the merchandise easily. Furthermore, up and down escalator traffic should be physically separated and should not lead into confined spaces. Traffic patterns must also be anticipated. In some buildings, the objective is simply to move people from one floor to another, but in others there may be a more specific requirement, such as funneling visitors towards a main exit or exhibit. The escalators must be designed to carry the required number of passengers. For example, a single-width escalator traveling at about 1.5 feet per second can move about 2,000 people per hour. The carrying capacity of an escalator system must match the expected peak traffic demand, presuming that passengers ride single file. This is crucial if there are sudden increases in the number of riders. For example, escalators at stations must be designed to cater for the peak traffic flow discharged from a train, without causing excessive bunching at the escalator entrance. In this regard, escalators help in controlling the flow of people. For example, an escalator to an exit effectively discourages most people from using it as an entrance, and may reduce security concerns. Similarly, escalators often are used as the exit from airport security checkpoints. Such an egress point would still generally be staffed to prevent its use as an entrance during times of light pedestrian traffic. It is preferred that staircases be located adjacent to the escalator if the escalator is the primary means of transport between floors. It may also be necessary to provide an elevator lift near the escalator for wheelchairs and disabled people. Finally, consideration should be given to the aesthetics of the escalator. Model sizes and other specifications, components, landing platforms, These two platforms house the curved sections of the tracks, as well as the gears and motors that drive the stairs. The top platform contains the motor assembly and the main drive gear, while the bottom holds the step return idler sprockets. These sections also anchor the ends of the escalator truss. In addition, the platforms contain a floor plate and a com plate. The floor plate provides a place for the passengers to stand before they step onto the moving stairs. This plate is flush with the finished floor and is either hinged or removable to allow easy access to the machinery below. The com plate is the piece between the stationary floor plate and the moving step. It is so named because its edge has a series of cleats that resemble the teeth of a comb. These teeth mesh with matching cleats on the edges of the steps. This design is necessary to minimize the gap between the stair and the landing, which helps prevent objects from getting caught in the gap. Truss. The truss is a hollow metal structure that bridges the lower and upper landings. It is composed of two side sections joined together with cross braces across the bottom and just below the top. The ends of the truss are attached to the top and bottom landing platforms via steel or concrete supports. The truss carries all the straight track sections connecting the upper and lower sections. Tracks. The track system is built into the truss to guide the step chain, which continuously pulls the steps from the bottom platform and back to the top in an endless loop. There are actually two tracks, one for the front wheels of the steps and one for the back wheels of the steps. The relative positions of these tracks cause the steps to form a staircase as they move out from under the com plate. Along the straight section of the truss, the tracks are at their maximum distance apart. This configuration forces the back of one step to be at a 90-degree angle relative to the step behind it. This right angle bends the steps into a shape resembling a staircase. At the top and bottom of the escalator, the two tracks converge so that the front and back wheels of the steps are almost in a straight line. This causes the stairs to lay in a flat sheet-like arrangement, one after another, so they can easily travel around the bend in the curved section of track. The tracks carry the steps down along the underside of the truss until they reach the bottom landing, where they pass through another curved section of track before exiting the bottom landing. At this point the tracks separate and the steps once again assume a staircase configuration. This cycle is repeated continually as the steps are pulled from bottom to top and back to the bottom again. Steps. The steps themselves are solid, one-piece, die-cast aluminum or steel. Yellow demarcation lines may be added to clearly indicate their edges. In most escalator models manufactured after 1950, both the riser and the tread of each step is cleated with comb-like protrusions that mesh with the com plates on the top and bottom platforms and the succeeding steps in the chain. Seeburger or step-type escalators featured flat treads and smooth risers. Other escalator models have cleated treads and smooth risers. The steps are linked by a continuous metal chain that forms a closed loop. The front and back edges of the steps are each connected to two wheels. The rear wheels are set further apart to fit into the back track and the front wheels have shorter axles to fit into the narrower front track. As described above, the position of the tracks controls the orientation of the steps. Handrail. The handrail provides a convenient handhold for passengers while they are riding the escalator. In an escalator, the handrail is pulled along its track by a chain that is connected to the main drive gear by a series of pulleys. It is constructed of 4 distinct sections. At the center of the handrail is a slider, also known as a glider ply, which is a layer of a cotton or synthetic textile. The purpose of the slider layer is to allow the handrail to move smoothly along its track. The next layer, known as the tension member, consists of either steel cable or flat steel tape, and provides the handrail with tensile strength and flexibility. On top of tension member are the inner construction components, which are made of chemically treated rubber designed to prevent the layers from separating. Finally, the outer layer the only part that passengers actually see is the cover, which is a blend of synthetic polymers and rubber. This cover is designed to resist degradation from environmental conditions, mechanical wear and tear, and human vandalism. In the factory, handrails are constructed by feeding rubber through a computer-controlled extrusion machine to produce layers of the required size and type in order to match specific orders. The component layers of fabric, rubber, and steel are shaped by skilled workers before being fed into the presses, where they are fused together. In the mid-20th century, some handrail designs consisted of a rubber bellows, with rings of smooth metal cladding called bracelets placed between each coil. This gave the handrail a rigid yet flexible feel. Additionally, each bellows section was no more than a few feet long, so if part of the handrail was damaged, only the bad segment needed to be replaced. These forms of handrail have largely been replaced with conventional fabric and rubber railings. Safety. Safety is also a major concern in escalator design. In India, where women wear saris, there are heavy chances of getting the pallu entangled in the escalator. As a result, a special sari guard is built into most escalators. There is a risk of foot injuries for children wearing footwear such as Crocs and flip-flops that might get caught in escalator mechanisms. This was due to the softness of the shoe's material combined with the smaller size of children's feet. Fire protection of an escalator may be provided by adding automatic fire detection and suppression systems inside the dust collection and engineer pit, in addition to any water sprinkler system installed in the ceiling. To limit the danger caused by overheating, ventilation for the spaces that contain the motors and gears must be provided, and small targeted clean agent automatic extinguishing systems can be installed in these areas. Fire protection of an escalator floor opening may be provided by adding automatic sprinklers or fireproof shutters to the opening, or by installing the escalator in an enclosed fire-protected hall. Accidents and litigation. Lessons of the King unregistered trademark S-Crossfire. The King's Crossfire of 1987 illustrated the demanding nature of escalator upkeep and the Devis unregistered trademark propensity to collect or fluff when not properly maintained. In the official inquiry that followed, the Fennell Report, it was determined that the fire started slowly, smoldered virtually undetected for a time, then exploded into the ticketing hall above in a phenomenon known as the A-OE trench effect and the Escalators unregistered trademark undercarriage. Approximately 8,800 kilograms of accumulated detritus acted as a wick to a neglected buildup of interior lubricants. Wood veneers, paper and plastic advertisements, solvent-based paint, plywood in the ticket hall, and melamine combustion added to the impact of the calamity. As a result of the report, older wooden escalators were removed from service in the London Underground. Additionally, sections of the London Underground that were actually below ground were made non-smoking. Eventually the whole system became a smoke-free zone. Litigation. In the 1930s, at least one suit was filed against a department store, alleging that its escalators posed an attractive nuisance, responsible for a child unregistered trademark S injury. Legislation and escalators. United States, despite their considerable scope, two congressional acts, the Rehabilitation Act of 1973 and the Americans with Disabilities Act of 1990, did not directly affect escalators or their public installations. Since Section 504 of the Rehabilitation Act included public transportation systems, for a few years, the United States Department of Transportation considered designs to retrofit existing escalators for wheelchair access. Nonetheless, Foster Miller Associates unregistered trademark 1980 plan, escalator modification for the handicapped was ultimately ignored in favor of increased elevator installations in subway systems. Likewise, the ADA provided more accessibility options, but expressly excluded escalators as accessible means of egress, advocating neither their removal nor retention in public structures. Codes and regulation. In the United States and Canada, new escalators must abide by ASME A17.1 standards, and old historic escalators must conform to the safety guidelines of ASME A17.3. In Europe, the escalator safety code is EN 115. History, inventors and manufacturers. Nathan Ames. Nathan Ames, a patent solicitor from Saugus, Massachusetts, is credited with patenting the first escalator in 1859, despite the fact that no working model of his design was ever built. His invention, the revolving stairs, is largely speculative and the patent specifications indicate that he had no preference for materials or potential use. though the mechanization was suggested to run either by manual or hydraulic power. Lehman-Suda. In 1889, Lehman-Suda successfully patented the stairway, an escalator-type device that featured a series of steps and links jointed to each other. No model was ever built. This was the first of at least 4 escalator-style patents issued to Suda, including 2 for spiral designs. Jesse Wilfred Reno, George A. Wheeler, and Charles Seeburger. On March 15, 1892, Jesse W. Reno patented the endless conveyor or elevator. A few months after Reno's patent was approved, George A. Wheeler patented his ideas for a more recognizable moving staircase, though it was never built. Wheeler unregistered trademark S patents were bought by Charles Seeburger. Some features of Wheeler unregistered trademark S designs were incorporated in Seeburger unregistered trademark S prototype built by the Otis Elevator Company in 1899. Reno, a graduate of Lehigh University, produced the first working escalator and installed it alongside the old iron pier at Coney Island, New York City in 1896. This particular device was little more than an incline belt with cast iron slats or cleats on the surface for traction, and traveled along a 25-degree incline. A few months later, the same prototype was used for a month-long trial period on the Manhattan side of the Brooklyn Bridge. Reno eventually joined forces with Otis, and retired once his patents were purchased outright. Some Reno-type escalators were still being used in the Boston subway until construction for the Big Dig precipitated their removal. The Smithsonian Institution considered reassembling one of these historic units from 1914 in their collection of Americana, but logistics and reassembly costs won out over nostalgia, and the project was discarded. Around May 1895, Charles Seeburger began drawings on a form of escalator similar to those patented by Wheeler in 1892. This device actually consisted of flat, moving stairs, not unlike the escalators of today, except for one important detail: the step surface was smooth, with no comb effect to safely guide the rider's feet off at the ends. Instead, the passenger had to step off sideways. To facilitate this, at the top or bottom of the escalator the steps continued moving horizontally beyond the end of the handrail until they disappeared under a triangular divider, which guided the passenger to either side. Seeburger teamed with Otis in 1899, and together they produced the first commercial escalator which won the first prize at the Paris 1900 Exposition in Ivry in France. Also on display at the exposition were Reno's inclined elevator, a similar model by James M. Dodge and the Link Belt Machinery Company, and 2 different devices by French manufacturers Copyright and Piat. Early European manufacturers, Copyright, Hockworth, and Piat installed its stepless escalator in Harrods Knightsbridge store on Wednesday, November 16, 1898, though the company relinquished its patent rights to the department store. Noted by Bill Lancaster in the department store, A Social History, customers unnerved by the experience were revived by shopmen dispensing free-smelling salts and cognac. The Harrods unit was a continuous lever belt made of 224 pieces, strongly linked together traveling in an upward direction, and was the first moving staircase in England. Hockworth received European patent rights for the FAT-REP in 1906. After the exposition, Copyright continued to sell its escalator device in Europe, but was eventually eclipsed in sales by other major manufacturers. Major competitors and product nomenclature. In the first half of the 20th century, several manufacturers developed their own escalator products, though they had to market their devices under different names, due to Otis' unregistered trademark hold on the trademark rights to the word OE escalator. New York-based Peel Company called their models the Motorster, and Westinghouse called their model an electric stairway. The Toledo-based Horton Elevator Company referred to their product as simply moving stairs. Manufacturing mergers and buyouts. The playing field narrows. Kohn and Schindler introduced their first escalator model several decades after the Otis Elevator Company, but grew to dominance in the field over time. Today, they, Mitsubishi, and ThyssenKrupp are Otis' primary rivals. Schindler now stands as the largest maker of escalators and second largest maker of elevators in the world, though their first escalator installation did not occur until 1936. In 1979, the company entered the United States market by purchasing Horton Elevator. 9 years later, Schindler assumed control of the North American escalator elevator operations of Westinghouse. Kohn expanded internationally by acquisition in the 1970s, buying out Swedish elevator manufacturer ACA Graham, and purchasing other minor French, German, and Austrian elevator makers before assuming control of Westinghouse unregistered Trademark European elevator business. As the last Big Four manufacturers held onto the escalator market, KONE first acquired Montgomery Elevator Company, then took control of Germania unregistered Trademark Renstein and Koppel-Rolltreppen. Model development and design types: cleat-type escalators. Jesse Reno's escalators did not resemble modern escalators too closely. Passenger feet tilted upward at an angle, and the treads consisted of cleated metal or wood. Reno worked on his own for several years, gaining success with installations from Toronto to Cape Town, South Africa. Similar units of the day by other manufacturers resembled conveyor belts more than moving staircases. For a time, Otis Elevator sold Reno's escalators as their own cleat-type escalators. Step-type escalators, Seeburger's model, bought by Otis, clearly became the first step-type escalator, named for its visual likeness to a regular staircase. The company later combined the best aspects of both inventions and in 1921 produced an escalator similar to the type used today, calling it an L-type escalator. It was succeeded by the M-type, the O-type, and current models by Otis such as the NCE-type escalator. Spiral helical escalators. Jesse Reno, in addition to being known for the first practical escalator in public use, also designed the first escalators installed in any underground subway system in the form of a spiral escalator at Holloway Road Tube Station in London in 1906. The experimental device never saw public use, and was forgotten for several decades. The remains of this are now in the London Transport Museum's depot in Acton. Also the first fully operational spiral escalator, Reno unregistered Trademark S design, was nonetheless only one in a series of several similar proposed contraptions. Suda patented two helical designs, Wheeler drafted helical stairway plans in 1905, Seeburger devised at least two different helical units between 1906 and 1911, and Gilbert Luna obtained West German, Japanese, and United States patents for his version of a spiral escalator by 1973. When interviewed for the Los Angeles Times that year, Luna was in the process of soliciting major firms for acquisition of his patents and company, but statistics are unclear on the outcome of his endeavors in that regard. The Mitsubishi Electric Corporation was most successful in its development of spiral helical escalators, and has sold them exclusively since the mid-1980s. The world's first practical spiral escalator, a Mitsubishi Model was installed in Osaka, Japan, in 1985. In use, a major planning advantage presented by spiral helical escalators is that they take up much less horizontal floor space than traditional units, which frequently house large machine rooms underneath the truss. Helixator, an experimental spiral helical escalator design which currently exists as a prototype scale model, could further reduce the floor space. The design has several innovations that offer the possibility of a continuous helix. Driven by a linear motor instead of a chain system, the helixator spreads the force evenly along the escalator path, avoiding excessive force on the top chain links and removing geometry, length and height limits. Freeform escalators, Levitator, a design originating at City University in London, can move in straight lines or curves with or without rising or descending. The returning steps do not move uselessly underneath the in-use steps, rather, they provide active steps for travel in the opposite direction. Etymology. Several authors and historians have contributed their own differing interpretations of the source of the word escalator, and some degree of misinformation has heretofore proliferated on the Internet. For reference, contradictory citations by 7 separate individuals, including the Otis Elevator Company itself, are provided below. Name development and original intentions. Charles Seeburger created the word escalator in 1900, to coincide with his Euro unregistered trademark S debut at the exposition in Ivosell. According to his own account, in 1895, his legal counsel advised him to name his new invention, and he then set out to devise a title for it on his own. As evidenced in Seeburger's own handwritten documents, archived at the Otis Elevator Company headquarters in Farmington, Connecticut, the inventor consulted a Latin lexicon, and adopted as the root of the new word, scala. As a prefix, e, and as a suffix, tor. His own rough translation of the word thus created was means of traversing from, and he intended for the word to be pronounced, ESA Euro to the first car la Euro unregistered trademark a Euro section TE unregistered trademark R. Escalator was not a combination of other French or Greek words, and was never a derivative of elevator in the original sense, which means one who raises up, a deliverer in Latin. Similarly, the root word scala does not mean a flight of steps, but is defined by Lewis in shorter Euro unregistered trademark SA Latin dictionary as the singular form of the plural noun scalae, which denotes any of the following: a flight of steps or stairs, a staircase, a ladder, or a scaling ladder. The alleged intended capitalization of escalator is likewise a topic of debate. Seeburger Euro unregistered trademark S trademark application lists the word not only with the E, but also with all of the letters capitalized, and he specifies that any other form and character of type may be employed without altering in any essential manner the character of the trademark. That his initial specifications are ostensibly inconsistent, and since Otis Elevator Company advertisements so frequently capitalized all of the letters in the word, suppositions about the capital a Euro unregistered trademark are difficult to formulate. Derivatives of escalator. The verb escalate originated in 1922, and has two uses: the primary, to climb or reach by means of an escalator, or to travel on an escalator, and the secondary, to increase or develop by successive stages. Spec. To develop from conventional warfare into nuclear warfare. The latter definition was first printed in the Manchester Guardian in 1959, but grew to prominent use during the late 1960s and early 1970s. Loss of trademark rights. In 1950, the landmark case Horton Elevator Company v. Seeburger precipitated the end of Otis's reign over exclusive use of the word escalator, and simultaneously created a cautionary study for companies and individuals interested in trademark retention. Confirming the contention of the examiner of trademark interferences, Assistant Commissioner of Patents Murphy Euro unregistered trademark S decision rejected the Otis Elevator Company Euro unregistered trademark S appeal to keep their trademark intact, and noted that the term escalator is recognized by the general public as the name for a moving stairway and not the source thereof, observing that the Otis Elevator Company had used the term as a generic descriptive term a Euro in a number of patents which had been issued to them and a Euro in their advertising matter. All trademark protections were removed from the word escalator, the term was officially genericized, and it fell into the public domain. Primary uses and application. Department stores shopping. As noted above, a few escalator types were installed in major department stores before the expo. Escalators proved instrumental in the layout and design of shopping venues in the 20th century. By 1898, the first of Reno Euro unregistered trademark S inclined elevators were incorporated into the Bloomingdale Brothers store at 3rd Avenue and 59th Street. This was the first retail application of the devices in the U.S., and no small coincidence, considering that Reno's primary financier was Lyman Bloomingdale, co-owner of the department store with brother Joseph Bloomingdale. Public transportation. The first standard escalator installed on the London Underground was a Seeburger model at Earl's Court. Noted above, London's Underground installed a rare spiral escalator designed by Reno, William Henry Aston and Scott Kietzman for the Holloway Road Underground station in 1906. It was run for a short time but was taken out of service the same day it debuted. The older lines of the London Underground had many escalators with wooden treads until they were rapidly replaced following the King's Cross fire, noted above. Other applications, factories and other industrial production environments, In 1905, the American woolen company unregistered trademark S. Woodmill in Lawrence, Massachusetts utilized Otis Seeburger type reversible escalators to carry its workers between floors 4 times a day. The machines did not run all day, rather, escalators ran solely to transport employees to from midday meals and in out of the mill. In its advertising, Otis Elevator Company hailed this unconventional use for its unique benefits to both workers and owners. The profitable and practicable feature of the escalator, from the viewpoint of the owner, is the increased efficiency of each operator due to the elimination of stair climbing. Military use. In San Francisco, an escalator at Hunters Point Naval Shipyard was used to convey personnel between the first and third floors. At the time of its construction in 1948, it was touted thus: "It is the highest lift of any industrial building in the world. It rises 42 feet." Escalators were also utilized on aircraft carriers such as the USA Hornet, CV-12, to transport pilots from ready rooms to the flight deck. Extant historic escalator models. A few notable examples of historic escalators still in operation include, Australia, Town Hall Railway Station, Sydney, Australia, Wynyard Railway Station, Sydney, Australia. Europe Street and a pedestrian tunnel underneath the Schelde in Antwerp, Belgium. This tunnel was opened in 1933. Tyne Cyclist and Pedestrian Tunnel, Tyne and Wear, England. These escalators, manufactured by Waygood Otis in 1951, were believed to be the longest single-lift escalators in the world, at the time of installation. Presumably the first escalators in Britain designed specifically for cyclists, they were also the longest in the United Kingdom. At most, they may be the longest extant wooden escalators in the world, though they are no longer in working order. Bormanskaya Metro Station in Moscow, Russia contains the oldest escalator of tonnel type still in use, with length of 65 am and vertical rise of 32.5 am. North America, Macy's Herald Square Department Store, Otis L-type units with wood treads and replacement metal treads, New York, New York, Kaufman's Department Store, 2 16-inch Otis L-type units with original floor plates, several 40-inch Otis escalators circa 1950s, Pittsburgh, Pennsylvania, Westfield San Francisco Center, chrome and glass escalator by Eleanor Lemaire for Otis, San Francisco, California, DeLand Pavilion Epcot, glass escalator by Otis. Has stairs next to them. Not single file but is separated, Tokyo Sesame Place glass escalator with Big Bird's mouth as the entrance. First escalator in a theme park, escalators, superlatives, longest systems, Central Mid-Levels Escalator, in Hong Kong. Tens of thousands of commuters travel each workday between Central, the Central Business District, and the Mid-Levels, a residential district hundreds of feet uphill, using this long-distance system of escalators and moving walkways. It is the world's longest outdoor escalator system, at a total length of 2,600 feet. It goes only one way at a time. The direction reverses depending on rush hour traffic direction. In December 2011, a network of 6 escalators of 1,260 feet length, equivalent to 28 stories high, was opened in Medellin, Colombia, offering the 12,000 residents of Comena 6-minute ride to the city center compared to their previous 35-minute climb on foot. Cascade, Yerevan, an escalator system of 774 ft length and 387 ft height. Ocean Park, Hong Kong, a long escalator system connecting 2 parts of the park, with an overall length of 730 feet. Longest individual escalators. World. The longest escalators in the world are installed in deep underground stations of the St. Petersburg Metro. 3 stations have escalators up to 137 am long and 68.5 am high, Ploshchad Lenina, Chernyshevskaya, and Admiraltyskaya. See also Kiev Metro in the Europe section. The longest freestanding escalator in the world is inside CNN Center, a unregistered trademark S atrium in Atlanta, Georgia. It rises 8 stories and is 205 feet long. Originally built as the entrance to the amusement park The World of Sid and Marty Krofft, the escalator is now used for CNN studio tours. Asia, the longest escalator in Bangkok, Thailand in Southeast Asia is in Bangkok Metro's Silom station. It connects the concourse level with Platform 1 which in turn connects to Hue Lam Phong. It is 43 am in length and 21.5 am in depth. The Rustavi station in the Tbilisi Metro has one of the world's longest escalators. It is 60 meters high and 120 meters long. Australia, the longest set of single-span uninterrupted escalators in the Southern Hemisphere is at Parliament Underground Railway Station in Melbourne. Europe, several metro or subway systems in Central and Eastern Europe feature very long escalators. The Kiev Metro Kriskatik station's lower-level second exit escalator lifts riders 65.7 meters, or 743 steps, up a 131.4 euro-long incline. In the Park Pobedi station of the Moscow Metro, the escalators are 126.8 am or 740 steps long, and 63.4 am high. It takes 3 minutes to transit. 3 stations in St. Petersburg Metro have escalators up to 138 am long and 69 am high, Ploshchad Lenina, Chernyshevskaya, and Admiraltyskaya. The longest escalator in Prague, and in European Union, is at the Náměstí Maru station at 285 feet long and 142.5 feet high. The longest escalator of a European shopping mall is at Myziel, Frankfurt, Germany, with a length of 150 feet. The tallest escalator on the London Underground system is at Angel Station with a length of 200 feet, and a vertical rise of 100 feet. The longest wooden escalators in the United Kingdom are at the Tyne Tunnel, with a length of 197 feet. The longest escalators in Western Europe are in the Stockholm Metro, at Vakarantsestraskigen with a length of 220 feet and in Helsinki Metro, at Kamppi Station with a length of 210 feet. The largest single truss escalator is in the Bentall Centre in Kingston upon Thames in Greater London, UK. It connects the ground floor with the second floor with only top and bottom supports. North and South America, the longest set of single-span uninterrupted escalators in the Western Hemisphere is at the Wheaton Station of the Washington Metro system. They are 230 feet long with a vertical rise of 115 feet, and take what is variously described as 2 minutes and 45 seconds or nearly 3.5 minutes, to ascend or descend without walking. Shortest examples, according to Guinness, the shortest escalator in the world is in the Okada shopping mall in Kawasaki, Japan. Its vertical rise is only 32.8 inches. Notable spiral escalator installations. Asia, Hyalok Place, Singapore, Jeddah Hilton, Saudi Arabia, Landmark Tower, Japan, Times Square Shopping Mall, Causeway Bay, Hong Kong, Lotte World, South Korea, the Venetian Hotel and Casino, Cotai, Macau, WTC Mangadua, Jakarta, Indonesia, Taipei, Taiwan, North America, Wynn Las Vegas, Nevada, United States, the Forum Shops at Caesars, Las Vegas, Nevada, United States, Westfield San Francisco Center, San Francisco, California, United States. The first such installation in the Western Hemisphere. River Rock Casino Resort, Richmond, British Columbia, Canada. The first in Canada. Bloomberg Corporation Office, New York, United States. Etiquette. On some busy systems, such as those in the UK, US, Germany, Taiwan and Hong Kong, there is a de facto standard policy of standing on the right. Often, this informal standard is reinforced by official regulations, though official enforcement is rarely required. In most of Japan including Tokyo, the policy is to stand on the left. However, in Osaka they stand on the right. Either way, the open side of the escalators is reserved for those riders walking and overtaking. There are informal or formal standards on smaller systems such as the Prague subway system and the Toronto subway. The etiquette in Australia and New Zealand is to stand on the left. See also. References and notes. External links, a video clip, Escalators with transparent sides showing the mechanism in operation. Winchester, Clarence, ed., How Escalators Work, Railway Wonders of the World, ppA 343 Euro 348. A illustrated description of escalators on the London Underground and their advantages over lifts.